Good afternoon, everybody. Welcome to a cold winter afternoon of Chem 170 with your host, me, Dr. White. It's winter out there. I don't know about you, but since we last met last Wednesday, I got to spend a lot of quality time with my snowblower and driveway. Hopefully, we won't have snow for a while. I can do without it. Thank goodness I know how to maintain my snowblower, which I think is about 22 years old, but it works like a charm. I've replaced a lot of stuff on it, but it works. All right, let's get to work. Couple things. First of all, one of you asked, and I appreciate it, I forgot to set properly the assignment area for the signature sheet. And let me just click that off. And so look at Blackboard. We're on school D2L. I said I'd do that. And let's do that right now. And hopefully everybody sees D2L Chem 170 on your screen. If not, yell out. And you should. Zoom just added this semester a new feature, which I can see what screen you're seeing. In the past, I'd ask thumbs up. All right. Now, if I go to view as a student, and if we click on assignments, you'll see the signature sheet. Please fill it out. If you do not have a scanner, I have files how to either take a picture and convert it into a PDF file, or you can use the application, the app Cam Scanner. And students have been using that for a while in my class. And do not buy the Cam Scanner app with all the bells and whistles. Just use the free version. It works well. And also you'll see, you can now see for this Wednesday, this is the lab we'll be doing. I have it both as a Word document and a PDF file. On Wednesday, I'll go through it. Now, since it's too dangerous to have you do chemistry, organic chemistry at home, I wouldn't, and you shouldn't. What I'm doing with the labs is I'll go through the labs just like if we were face to face. I call that my introduction or setup. And then normally, if we're face to face, you go into lab, do something. In other words, this Wednesday, you would have taken some melting points and gotten data and answer questions that are in those labs. Now, I've been able to find on YouTube, I think everything's on YouTube except my high school graduation. But anyways, where they show you people doing melting points. And that way you'll get a feel how to do it. But the most important thing is in our labs, and even when we're face to face, it's more how you interpret what you learn. And that mental experience you will get this semester, but you will not be doing any actual chemistry, manipulating chemicals or whatever in your home. But you'll get the same experience, just about. All right. Now, I promised, and Dr. White always keeps his promises. I can't ever remember breaking a promise, at least intentionally, that right now I said I'd go through the alkanes problem set, so I will. Now, the way I do problem set is I'll do a page at a time, 1 or 2 problems. If you have a question, ask. You want me to do a problem I didn't do? Ask. In case you forgot, remember, in my class, in my world, there's no such thing as a dumb question, ever. Always feel free to ask questions in my class, and never, ever, ever, I don't know why, well, I do know why, unfortunately, you never have to say you're sorry for asking a question in my class, never. All right, let's get to work. All right, everybody see alkanes problem set on your screen. Give me a thumbs up if you can see it. Thank you. All right, let's do a couple. And the question is, how many carbon atoms are in the longest chain of the following? And this is an important skill in order to learn how to name organic molecules. And if we look, I didn't even put in the hydrogens to not confuse you. And let's look at G. If we count across 1, 2, 3, 4, 5, 6, that's one chain. If we start the same way, and you could have done the other way too, 1, 2, 3, 4. Now, if you notice, carbon 4 is bonded, connected, that's what the line tells us, to carbon 5 on the right. But you can also count down carbon 4's bond to this carbon 5, which is bond to this. So it's 6. So those two are the longest chain. There's another chain starting here, 1, 2, 3, 4, 5. That's shorter. So the longest chain is 6. Now let's look at F. Now F gets a little complex. Remember, you're being asked to find the longest chain. And if we count across 1, 2, 3, 4, and I don't have number 5, 6, straight across would be 6 carbons. Now, if we count 4, then down to 5, then to 6, then to 7, then 8, then 9, that's the longest chain. Even though it sort of zigzags, I like my special effects. That was awful, sorry. But anyways, it's still the longest chain because it's like a bicycle chain. You can flex it all different ways. So an important skill you should know is how to find the longest chain. Now, number 2 says, give the IUPAC name for the following. When you see the word or the acronym IUPAC, that means the official name, even though I'll never ask on tests, but I like to say that's International Union of Pure Applied Chemistry. So how do you do this? First, you find the longest chain, unbranched chain. Na, oh, look, it's your old friend propane. And as I told you a while ago, hopefully you have memorized this chart. And hopefully you've memorized this chart. You should know propane, 3 carbons. So as soon as we see 3 carbons straight chain, that's propane. Now, if we look at C, count the carbons, not hydrogens, they're 9. And if we look at that same table, which hopefully you know by the end of this week, as well as you know your own name, and I'm assuming all of you know your own name like that. Oh, it's broken. They're broken. I got to change the batteries. Hold on. No, it's broken. Like that. But anyways, if we look at 9, that's no name. Now, one of the things I have here, and we're not going to use this until way late in the semester, like week 15, is I show parentheses, where inside the parentheses, you see CH2 subscript 7, meaning there's 7 of them, 1, 2, 3, 4, 5, 6, 7. And that's another way of writing no name. Now, I won't do that on the test until we get into chapter 15, and I'll come back and review this because I'm not going to waste my time, and I don't think you should, when you have to write out 16 CH2s. Did I tell you organic chemists are lazy? We are. All right, now let's get some interesting thing. Now, if we look at D, oh, wait, there's something hanging out here. So you find the longest chain. There are 2 ways of counting it, 4, and the root name is butane. 4 carbons. You've learned this table. 4 carbons, butane. Remember, if you write down butane and number 4 and say it, write it down and say it again, and do that 5 times, it burns it into your brain. It's worked for many years for my students and does a better job than flashcards. But I've had a few students that flashcards work for them. But writing it down seems to be a very excellent way to memorize that. So 4 carbons, butane. We have left over CH3. On a PDF file, I can't use my marker. At least I haven't found a way to do that, my whiteboard, like I can do on a MS doc. But anyways, CH3. And the other thing, and you have learned that here are key alkyl groups. CH3, and the line says bonded to something else is a methyl. 2 carbons, N carbon bonded ethyl. 3 carbons, there's 2 possibilities. The N carbon bonded to a chain or ring is N-propyl. The middle carbon, isopropyl. There are 3 possibilities, but I'm only teaching you 2, because I'll be honest, the third one I've never used in the decades I've been working in the chemical industry. Yep, decades. And N carbon of 4 is N-butyl. 3 carbons bonded to a center carbon, bonded to a ring or a long chain, tert, or later on this week, I'll get lazy and just like most organic chemists call it tert-butyl, T-butyl. By the way, tert is short for tertiary 3. You should know this chart as well as you know your own name. So we have a methyl group, so it's methylbutane, and then you number from the end of the chains the direction to give the alkyl groups the lowest number, this case 1, 2, it's 2-methylbutane. Now, I just wanted to show you an E. All I've done is flip the molecule 180 degrees, whoop, like that. And guess what? It's got the same name. All right, let's look at G. The longest chain going across is 9. Remember, you learned in the first question, I don't have an example here, but you can have the longest chain not being straight across. And then 9 carbons, no name. That's this chain right here. We have a CH3, 3 carbons, CH3, CH, CH3. And this is a methyl group. This is an isopropyl group. 3 carbons, center carbon bonded to the chain. And we start from here, it's a methyl group is on carbon 2, isopropyl on carbon 4. You start the other way, 1, 2, 3, 4, 5, 6 for the isopropyl, 8 for the methyl. You always start from the end. Now, common mistake on test number 1. I'm telling you this, they don't make it. Students look at this and say, oh, I'll call the methyl group 1. No, it's on carbon 2. You can only start from the ends of a chain. Now, I'm not going to hold you to the alphabetical rule. On my keys, I hold myself to the alphabetical rule. But if you had put down 4 isopropyl, 2 methyl, no name, I would have given you full credit. Now, let's look at H. Everybody look at H. And if you look at H, you see, ooh, this is a ring. Every bend in a line is a carbon, because with the line method, we don't show carbons or hydrogens. Every bend in a line is a carbon. 6 bends, hexane. It's a ring, cyclohexane. Common mistake on test 1 is students forget the cyclo. That's wrong. Your hand and foot are different, even both have 5 digits. I guess our toes called digits. Well, somebody correct me if I'm wrong on that. And therefore, it's cyclohexane. When there's only one alkyl group on a ring, you do not use a number. And if you do, I'll mark it wrong. when you have a ring, you only one alkyl group, you don't use a number. And here we have a ring, 6 carbons, cyclohexane, isopropyl group. Now, if we look at K, when you're numbering alkyl groups on a ring, the alkyl group with the highest alphabetical priority, closest to the front of the alphabet, gets the lowest number, and you go clockwise or counterclockwise to give the alkyl groups the lowest number. 5 carbons in a ring, pentane, ring, cyclopentane. I have an ethyl and a T-butyl or tert-butyl. Remember, this is why I'm going to tell you why I don't ask you to learn the alphabetical rule, or I won't grade it, because prefix is tert-butyl is actually considered a B, which is why it gives the number 1. The ethyl is 2. Now, there are 3 other answers that I would accept on my test. If you have the 2 ethyl, 1 tert-butyl, if you have 2 tert-butyl, 1 ethyl, or if you have 2 ethyl, 1 ethyl, 2 tert-butyl. But the one I give is the correct one based on the IUPAC rules. Now, there are 2 types of nomenclature question I ask on my test. One is this one. Give the IUPAC name for the following molecules. The other type of nomenclature, remember nomenclature is just a fancy word for names, is draw the condensed structures for the following IUPAC molecules. Now, condensed means you don't show the carbon-hydrogen bonds, like I have CH4. How do you do that? Well, butane, you've learned this table, if I can find it. Butane, 4 carbons. Therefore, I have my 4 carbons. Remember, how many bonds to carbon? 4. How many bonds? 4. 4. Does it seem like it's coming right at you? 4 bonds to carbon. That's going to be our friend always. All right, now, if we go to F, 2,3-dimethyl cyclohexane, you start from the right and move left. Hexane, 6 carbon chain. Here's my 6 carbons. By the way, pro tip, put the hydrogens in last. Then on carbons 2 and 3, well, methyl means CH3. Remember, di means 2, tri means 3. And they're on carbons 2 and 3. Now, if we look at G, butane, 4 carbons, cyclobutane, a ring with 4 carbons, you call that a square, I call that a ring. Now, I did make a mistake on I, how it should have been 1 tert-butyl, 2 ethyl, but you still should have been able to. Start from the right, pentane, cyclo, 5 carbon ring, on 1 carbon is the T-butyl group, another carbon right adjacent is ethyl. There are many ways of writing it, and I'll bet most of you probably wrote that one this way. And remember, molecules rotate, and that's all I've done in my answer, flipped and rotated it. But anyways, that's how you do it. Oh, we're here. How many carbons are in the longest chain for this molecule? Your turn. I gotta share the fun, and I will, and I am. And thank you to everybody who turned on your webcam. And thank you to everybody who showed up today. Over the last couple of years, teaching this on Zoom because of the pandemic, it's amazing where people have been logging in. I had one login user from the ECC library. I had one who was an ambulance driver, and in between runs would be in his ambulance on his cell phone. All right, let me check if you're done. All right, everybody's done, so it's my turn. If I go across 1, 2, 3, well, that's one chain. 1, 2, 3, 4, 5, 6. That's the second chain. 1, 2, 3, 4, 5, 6. And that's the third chain. So the longest chain is 6. Remember, the math is real hard. You have to know how this part of the semester count up to 10 and know what numbers are smaller or greater in the range from 1 to 10, and also how to add and subtract up to 4. And after test 1, you'll understand my practice problems and why I call them practice problems. And I didn't have a chance yet today, but by tomorrow morning or sometime tomorrow morning, the presentation, which I took out of the video on the method, test anxiety, I will post as a private video, and I'll send out an email with a link to that on YouTube. And if you want to go back and watch it again, you can. And I'll leave it up for a couple of weeks and then I'll delete it. All right, your turn. Give the IUPAC name for the following. Bet nobody warned you. I exercise your brain in my class. Or better yet, hopefully you are. And thanks for making me a YouTube star. I assume, I shouldn't say I assume, it looks like a lot of you are looking at the videos, and hopefully that helps you. Oh, I forgot to ask. Did any of you, when you drove by a gas station, think of alkanes? Oh, no. Did anybody happen to see a carrot or tomato and think of alkenes, double bonds? Or remember, organic chemistry is all around you. I stole that from SpongeBob, and it won't hurt you to think about it. Trust me, I'm an organic chemist. That work? All right. That's not what I wanted to do. This is what I wanted to do. It's my turn. All right, if we look at this chain, first thing you have to do is find what is the longest chain. We go across 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So across 10 carbons. If we start at 1, we can go 2, 3, 4. Nope, that's smaller than 10. We start here 1, 2, 3, 4, 5, 6, 7. Nope, that's smaller than 10. And if we start at the CH3 group underneath the long chain, 1, 2, 3, 4, 5, 6, 7, 8. So the longest chain is 10. And you have learned, hint, that 10 is decane. As soon as I say that, this is spoken for. Oh, we've got something left to take care of. Alkyl group, CH3. Oh, it's your old friend, the methyl group. This is methyl, this is ethyl. Now, what carbons are they on? Here's carbon 1. Remember, you always have to start from the end. 2, 3, 4, 5. If I start that way, it's 5. If I start this way, it's 1, 2, 3, 4, 5, 6, 7, 8. Which is the smaller numbers? 3 and 5, 6 and 8, and hopefully all pick 3 and 5. So the ethyl group is on, oops, wrong number. The ethyl group is on 5, and the methyl group is on 3. So that'd be 3 ethyl, 5 methyl decane. Oh, let's do another one. And here's another one for you to have fun with. If I say fun enough times, you might believe me. It is. Reactions are more fun. Again, the question is, give the IUPAC name for the following. You're doing organic chemistry, and hopefully it isn't painful. Yeah, it looks like everybody's done, so it's my turn. Oh, we've got a ring. Did I tell you Dr. White, me, and Mother Nature love rings? They do. She does. I do. All right. How many carbons in that ring? Count them. Bens, 1, 2, 3, 4, 5, 6. That's hexane. But it's a ring, so you need the prefix cyclohexane. And we have an alkyl group, 4 carbons, center carbon attached to 3 other carbons. And hopefully you've learned this table, and that's a tert or T-butyl group. It's one of the last times you'll be seeing me write tert. And by Wednesday, I'll be T-butyl. And there's no number. That's important. When there's only one alkyl group on a ring, it's always going to be on carbon 1, no matter where you draw it. And therefore, everybody knows that, so we don't need the number. So that's tert-butyl cyclohexane. All right, let's do 2 more, because practice is good for your grade. I'm sure you want to get a good grade. I hope you do. I want you to. All right. Here's one for you. Draw the structure of 2,4-dimethyl octane. Anybody happen to think of the octane number? Talks about organic chemistry when you buy gasoline. Remember your friend. 4 bonds to carbon. And I try and give everybody time to finish. And it looks like everybody finished. So how do you know what to draw? You start from the right and move left. Octane, 8 carbon straight chain. Eight carbons. Methyl, CH3. Di means 2. And I don't have it here, but tri means 3 groups of that alkyl group. There's tetra, but I've never seen that in my career, other than a real bad joke. I'm not going to do you. So dimethyl means 2 methyl groups, and it's on carbon 2 and 3. I count, or 2 and 4, I'm sorry. 1, 2, 3, 4, methyl, methyl. And there are 4 bonds to carbon. Remember, it's now your solemn responsibility, being a member of my class, if I make a mistake putting in the number of hydrogens, correct me, please. And that's how you draw it. Oh, let's do one more. And here we have 1 ethyl, 3 N-propyl, cyclohexane. And the question is, please draw the following using condensed form. And one of the reasons I'm taking time to go over nomenclature, because we're building, or I'm building in you, and you're building the foundation, which you'll see other nomenclature is built on this. As I've already mentioned, test 1 will be 50% nomenclature. Remember, that's naming. Test 2 and 3 will be about 38 to 40% of the points out of 100 nomenclature. It looks like everybody's done, so I better get to work. How do you decode this to know what to draw? Start from the right, move left. Hexane, 6 carbons, but cyclo tells me I have a ring. And each bend of the line is carbon. And carbon 3 is an N-propyl, carbon 1 is an ethyl. So I'll do 1, 2, 3. It doesn't matter which side, right or left. I put the second carbon here, N-propyl, 3 carbons in a straight chain. Remember, there are 4, yes, 4 bonds to carbon. And that's 1 ethyl, 3 N-propyl, cyclohexane. All right, let's go back to the problem set because we're not finished with it yet. Remember, these problem sets and the problem set answers are in D2L. In case of the problem set answers, they're in the folder that says cleverly hidden problem set answers. All right, look at question 2. Give the reaction product or products for the following reactions. And on test 1, 40% of the points will be these type of problems. Test 2 and 3, well, we'll spend more time on reactions, less on nomenclature, and that will increase to 60%. Well, let's look at the first one. We have a molecule plus oxygen, and the question is, what does it make? How do you do that? And you're trying to find what are the product or products. You look at this molecule, say, wait, that's only carbon, hydrogen, carbon, carbon, single bonds, that's an alkane. But it also could have been a cycloalkane, but it's not. And I'm reacting with oxygen, and what do I get? Carbon dioxide plus water. This you need to memorize. There's no sugarcoating around it. And therefore, since I have an alkane, oxygen, I'm going to get CO2 plus water. And that's how you do it. Now, listen carefully. Some of my best students I've ever had, when you look at their test, underneath each problem like this, they will write the general reaction to help them get the answer. Some of my best students I've ever had, they never write it underneath, but it's in their brain, obviously, because they get high scores. So either way, you want to write it underneath, like I'm going to be doing when we learn more in class, you can, or you don't have to. It works both ways. But how do you memorize this reaction? Right here, general reaction, you write it down and say it 5 times. You can use flashcards, but the repetition I have found for most students works much, much better. And that's how you do it. Now, if we look at B, that's an alkane, octane, oxygen. Guess what? It gives the same thing. And C, cyclohexane, that's a cycloalkane. That also with oxygen will combust. This is called combustion, and that gives CO2 and water. Remember, in my class, you never have to balance a chemical equation. In fact, in organic chemistry, unless you're doing calculations for charge weights, how much of this chemical and this chemical you have to put together to make another chemical, how much of, you don't need to balance chemical equations. Like I said, organic chemists are lazy. Unless we have to, we don't. We're lazy. All right, any questions on any of the alkanes? Going once? Going twice? I went to a lot of auctions with my brother-in-law when he was alive, God bless his soul, and he owned a company, a bindery and folding company. And when certain companies would go out of business, we'd go to the company, he'd take me along, it was fun. And I'd go to the auctions, the first one I ever went to, he said, don't say anything, keep your hands in your pocket. And when the auction is going on, don't make any sudden moves. Otherwise, you've just spent $50,000 on a piece of equipment. All right. On last Monday, we were talking about the alkenes. Remember, alkene is a carbon-carbon double bond, the 2 lines, each representing a pair of electrons. That's a double bond. And I talked about cis and trans isomers. And cis means either 2 of the same atom or group are on the same side of a plane. orthogonal to the double bond. I'll show you how to see that easy. And trans means two atoms or two groups, the same, one on each carbon. The double bond is on opposite sides. And later in the semester, I'll teach you about cis and trans fats. But if you've been following health the last number of years, medical science has found trans fats are not as healthy for you as cis. Why is that so? I don't know. I'm not a medical doctor. I know the organic chemistry, but it's important enough that major companies like McDonald's and food companies have switched to cis fats. But let's take a look at the following. And tonight at midnight, I'll be giving speed structure drawing lessons. No, I won't. But just a reminder, don't forget tomorrow from 6 to 7:15 and Wednesday from 6 to 7:15. I have my office hours. If any of you think a better time for office hours, or if you can't come and need help, email me and I'll see if we can set up a Zoom meeting so I can help you. All right, the question would be, give the IUPAC give the IUPAC name for the following. I'll do this on after the break. We'll come back and let you try it. And how do you do this? Oh, a double bond. Find the longest chain with both carbons of the double bond. 1, 2, 3, 4, 5, 6. This would be 7. Where I go 7, 8. So the longest chain is 8 octane. But a double bond has an ending of ENE. You drop the ANE from octane, put in ENE, octene. What's the lead carbon of the double bond closest to the end of the chain? In this case, it's 3. So it's 3-octene. And then here's a plane. And notice I have these two hydrogens, one on each carbon of the double bond, and they're on below the same side. Oh, look, someone was nice enough to say same side cis, opposite sides trans. So now this is cis 3-octene. And as soon as I say that, oops. All that's spoken for. Are we done? No, look what's left over. It's your good friend, the methyl group. And what carbon is it on? 6. So this is 6-methyl cis 3-octane. Wow, that's a mouthful, but that's the name. And if I look at the clock, it's time to take a break. Let's take a 5-minute break. I'll come back in 5 minutes and we'll continue on this cold afternoon with some organic chemistry that hopefully warms you up. Boy, that was hokey. See you in 5. Time to get going. And welcome back, everybody. All right, let's look at the whiteboard. And it's time for you to have fun. And the question is, what's the IUPAC name for the following? And as always, if you can turn on your webcam, please do. And what we're doing, in case you came back late, what's the IUPAC name of the molecule on the screen? All right, I think everybody's done, so I can get to work. In case you're not, you can always watch the video and stop it and finish and do it on your own again. All right, let's take a look at this. Look for what's different from now on. When you look at a molecule, organic molecule, look for what's not carbon, what's not hydrogen, or what's not a carbon-carbon single bond. We have a double bond. And how many carbons in the longest chain? 1, 2, that includes both carbons in double bond. 3, 4, 5, 6, 7, 8, 9, or I could go 7, 8, 9, 10. And hopefully you all agree 10 is larger than 9, so the longest chain is 10. that's decane. But since we have a double bond, drop the ane ending in decane and replace it with ene. Ene tells me I have a double bond. Now, what carbon of the two carbons is closest to the end of the chain? We start from this side, it's carbon 2. So that's 2-decene. If I have a plane right here, or a line, or your finger or pencil, notice the hydrogens, one on each carbon, are an opposite size. And same side is this, opposite side, trans. Well, those are below and above, if I could put my hand there, or the line, so that's trans. So it's trans 2-decene. As soon as I say that, all that's spoken for. Am I done? No. I have an alkyl group. 2 carbons is ethyl. And hopefully you've learned the alkyl group table. If not, do it this week. This is 1, 2, 3, 4, 4, 5, 6, 7. And therefore, that's 7-ethyl trans 2-decene. Actually, you don't need the dash there. I put them in accidentally sometimes. You did or didn't on a test, I wouldn't care. And that's how you do it. Let's go through. How did I do that? Found the longest chain with both carbons at a double bond. 10 carbons, decane. Double bond, drop the ane ending, decene, and replace with ene. What's the lead carbon of one of the 2 double bonds close to the end of the chain? We start from this side, it would be 2. We start from this side, it'd be 1, 2, 3, 4, 5, 6, 7, 8. And hopefully you agree 2 is smaller than 8. So it's 2-decene. On each of the carbons of the double bond on opposite side, I have a hydrogen that's trans, and then the ethyl group is on carbon 7. And that's how you do it. All right. Now, one of the things I don't have a slide here for, bad Dr. White. Nope, I don't. So I'll do it the old-fashioned way on the whiteboard. Now, if we look at this molecule, question is, what's the IUPAC name for the following? And we have a ring. How many carbons? 1, 2, 3, 4, 5. And look, 2 lines between the carbon 2 and 3 means that's a double bond. So how do you name this? You name the ring. 5 carbons pentane, a ring, cyclopentane. But for a ring, the ane ending is dropped and replaced with ene, just like for acyclic. So this is cyclopentene. Now, when you have no other functional groups, which for this class, the way I teach it for 1 semester, we won't, one of the carbons has to be always one of the double bond. and the other carbon has to be 2. When we have a double bond in a ring and no other functional groups, one of the carbons has to be 1. Remember, every bend of the line, I'll call this 1 and the other 2, or it could have been the other way. Since everybody knows that, you don't need a number. It's cyclopentene. Now, unless you get the very, very large rings, and I'm guessing now, and I'll stress that guessing, because it's been decades since I saw a rare example. I think you need 18 carbons or more in a ring, which is very, very rare. You can't have a trans bond in a ring. You can't have it in 4, 5, or even 6. And therefore, everybody knows that, and I don't have to put cis. So I'm done. This is cyclopentene. Now, again, drop the A and E ending, put an E ending. For ring, don't forget the cyclo. One of the carbons is always 1, the other is 2. And you don't have to. Your turn. Give the IUPAC name for this ring. Oh, I gave it away partially for this compound. And one of the things I'm secretly doing is training you to look at organic molecules, look for what's different, understand what is that difference, and how to name that. Am I sneaky or what? And for those who are finished early, please be patient. I try and give everybody time to finish. And it looks like everybody's finished. So if we look at this molecule, what do I see? A ring. How many carbons? Every bend in a line is a carbon. 6. That's hexane. Oops. And it's a ring, cyclohexane, but the A and E ending, because I have here a double bond. How do you know it's a double bond? Because between these 2 carbons, there's 2 lines. And you take the A and E ending at the end of cyclohexane, drop it, and replace it with E and E. And this is cyclohexene. Now, let's look at this one. Now, again, what's the IUPAC name? We have a ring, 5 carbons with a double bond, 2 lines, says cyclo. Pentane becomes pentene, cyclopentene. Now, I have a methyl group. Now, here's where it gets interesting. One of the carbons has to be 1. The other of the double bond carbons right here has to be 2. So if I do it this way, the methyl group is on carbon 3. Now, common mistake, students make this 1 and say this is 2. No, it's got to be. Now, if I call this 1 that 2, those are the only 2 ways you can number the double bond. And notice in black, the methyl group is on carbon 3. And if I count using blue, it's on carbon 5. And always in the IUPAC rules, you name or number in such a way that all alkyl groups get the lowest number. And here's one for you to have fun with. What's the IUPAC name for the following molecule? And thank you all for answering the poll. When you're done, we're in a classroom. I'd say when you're done, look up and smile, or actually I can tell when students are done. So it looks like everybody's done. My turn. What do we have here? Ooh, a ring, but we got a double bond. Remember, between these two carbons, two lines, double bond. How many carbons? 1, 2, 3, 4, 5, 6. Every bend in a line is a carbon. That's cyclo. Remember, for rings, you need the prefix cyclohexane. But double bond, drop the ANE at the end of cyclohexane and replace it with ENE ending. So that's cyclohexene. In a ring, you don't use in my classes or trans. And I'll be honest, in the last, I don't know how many decades, I have never seen anybody have an article where they had a trans double bond in a ring. But anyways, so you don't have to put cis or trans. Also, since there are no other functional groups, one of the carbons of double bond has to be 1, the other has to be 2. And if we number the way we have on carbon 4, we have an ethyl group. Now, if we number the other way, this would be carbon 1, 2, 3, 4, 5. So the correct way would be where you get the lowest numbers for the alkyl group. So that's 4-ethyl and black cyclohexene. And that's how you do it. Now, there are two types of nomenclature questions. And by the way, in a little while, we'll get into the good stuff, reactions, but this is important for the foundation because this is how organic chemists communicate. And the question is, draw the following. And I'll do one, then you know I'm going to share the fun. And how do you decode this to know what to draw? Start at the end on the right, move left. ENE ending means double bond. If that were ANE pentane, that's 5 carbons. So you have a 5-carbon chain, and first carbon, and remember the bond angle is 120 degrees. Carbon 3 and carbon 2, 1, 2 is my double bond. Notice it says cis. So that means the hydrogens, one on each carbon, are on the same side. And then 3, 4, 5. And there are 4 bonds to carbon. And that's how you do it. Again, pentane, double bond, ene ending, that were A and E, pentane, 5 carbons. The double bond starts on carbon 2, and it's cis. Remember, cis is same side, trans is opposite. And here's one for you to do. Trans 3 heptene. Draw that structure, please. All right, I think everybody's done. So it's my turn. How do you decode this? You start from the right, move left. En ending tells you there's a double bond. And for ane, heptane, hopefully you learn that's 7. So this 3 tells you the double bond starts at carbon 3 and it's trans. 1, 2, my double bond. Now trans means I have that opposite hydrogens, then 1, 2, 1, 2, 3, 4, 5, 6, 7. Nope, I counted wrong. 1, 2, 3, 4, 5, 6, now 7. If I ever count wrong, please let me know. And remember, there are 4 bonds to carbon. Let's review. Carbon 1 here has 1 bond to it. 4 minus 1 equals 3. So that's how I get 3 hydrogens, and I'll do the rest. And that's how you do it. Oh, let's do one more. And there you go, 4-isopropyl cyclohexene. And the question is, draw the following molecule. Your turn. All right, my turn. How do you decode this? You start from the right and move left. EN ending, double bond. There were ANE, cyclohexane, hexane 6, cyclo, is a ring. And it's got a double bond. I'm going to put it here. I could put it anywhere. All you're just doing is rotating it. And one of these is 1, the other 2. This would be 3. This is carbon 4. And I have an isopropyl group on carbon 4, isopropyl, 3 carbons. The center of 3 carbons is bonded to the ring. And that's how you do nomenclature of double bonds. Any questions? I'm all ears. That's one of the interesting things of life. I don't know if you're familiar, that one of the parts of your body that keeps on growing is your ears, which is why I'm older. I got bigger ears. I shouldn't have said that. All right, let's get into the good part of organic chemistry. I mean, the fun part. But then again, don't forget, I'm a synthetic organic chemist. That's my training, my PhD, and a time I spent in industry, and I still consult in that area, and I'm teaching it. And synthesis means to make. How do you make things? Think about the soap you used, hopefully, to wash your hands today, fabric softener, the gasoline and the additives it has, a whole bunch of stuff. That's all made by chemical reactions, and most of that is organic chemical reactions. And I'll be teaching you general reactions that are the building blocks. Think of the general reactions as different tools organic chemists use to make things. Just like if you were a carpenter apprentice, you learn how to use 2x4s, 1x2s, nails, screws, bolts to build things. Well, same thing we do, except we use general reactions. Now, coming chapters, and this one is going to start now, I will be teaching you some general reactions. Now, since we don't have other functional groups yet, normally how do you make a functional group? Then how do you react it? That's the real good fun part. But for this first one, let's just talk about reactions. Let me just do one thing. All right, so everybody see addition reactions on your screen. This you don't have to write down. Now, an alkene undergoes addition reaction where the pi bond is broken and 2 sigma or single bonds are formed. I'll never ask you on a test, what's an addition reaction? Now, let me remind you, you should know this. A double bond has 1 pi bond and 1 sigma bond. Here's a different way of writing a double bond. Now, one thing you'll see here is the letter R. And what R means is anything with carbon hydrogens and carbon-carbon single bonds. Now, everybody, I think, has math, and this will never be on my test. If you had x plus y equals 10, well, what are x and y? They're variables, and in our case, whole numbers. If x is 2, y is 8. If x is 5, y is 5. It can be numbers. Well, in organic chemistry, we use the letter R. And why? Well, I've never found. I actually spent one Saturday afternoon, about an hour, trying on Google and other places to find out who came up with using the letter R, and I couldn't. Either I just wasn't doing a good job, or it's just never been recorded. But that means anything with 1, a 10, 1,000 carbons. And what this really means is an addition if I have a double bond and add to something called AB, I'll break the pi bond. Remember, there's a pi bond and a sigma or single bond. And each carbon of the double bond gets something. And this is called an addition reaction. And you don't have to write, well, you could write it down, but, and don't forget, I have the fastest mouse wheel finger this side and the other side of the Mississippi River. So good question. Can you go back to the previous slide? I always will. Always. Now, this is very important. In this class, carbon-carbon sigma bonds or single bonds are almost never broken, except for combustion and a reaction, which I already taught you, and alkenes reacting with ozone, O3, which I'm not going to teach you. There are one or two others, but it's rare. Your friends this semester, first of all, how many bonds to carbon? 4. Second of all, now, do you break carbon-carbon single bonds? No. I'll say that again in slow motion. Do you break carbon-carbon single bonds? No, you don't, and you don't. And once I started teaching that, the first year I was teaching organic, my students' grades went up significantly because they were doing some of the weirdest things to carbon-carbon single bonds. And by saying, do you break carbon-carbon single bonds? No, except for combustion. All right, it's time to have some fun. Our first real organic chemistry reaction that can be used to make things, even though combustion is important. You can tell I'm more excited about this. Now, I'm going to be talking about the names of different reactions. I will never, ever ask on a test or a final, what's the name of a reaction? Now, the first one is hydrogenation. This is adding hydrogen gas. And actually, I should have put here hydrogen gas, which is H2 to a double bond. And you need a catalyst such as platinum, palladium, or nickel. Now, I'll never ask, but a catalyst is something that makes a reaction go quicker, but is not consumed. And in hydrogenation, and I did a lot of these in industry, both as a research chemist, 2 years I was a research chemist, then when I was a research and development manager, senior manager, I had chemists working for me do hydrogenations. If you don't have a catalyst, you can wait a month or two before something happens, maybe longer. You do have a catalyst at a certain higher temperature, about 140 degrees C, it's done in 4 hours. That's why we use catalysts. So let's look at hydrogenation. And a better way of remembering the reaction for your list of reactions, I have a double bond, and this means any double bond, any molecule that has a double bond, and I add hydrogen gas and a catalyst, and the catalyst, and I use CHM for abbreviation, can be nickel, platinum, or palladium. And what happens is, remember, this is one pi bond, and this is one sigma bond. You break the pi bond. Notice there are 2 lines between these 2 carbons now. There's only one. And each carbon of the double bond gets a hydrogen. And this is called hydrogenation. And I have supervised running this reaction up to 40,000 pound batches. If you've ever seen a tank wagon that delivers the vehicle that delivers gasoline to a gas station full, that's 5,000 gallons, 40,000 pounds, which is pretty big scale and fun. So double bond, hydrogen catalyst to break the pi bond, and each carbon double bond gets a hydrogen. Now, on a test, I'm never going to ask you what's the general reaction of hydrogenation. Here's the fun part, or sometimes students don't like it. I'm going to ask, give the organic product or products for it. Now, one thing, let me remind you. Here I have a general reaction, A plus B makes C. A and B are the starting materials. Or the reactants. If you're in industry like I have been for many decades, you'll call it starting materials. C is the product. This will never be on a test. Now, organic chemists are lazy and sometimes will write it this way. And this means the same as this. A plus B makes C, which is how I've wrote it here. All right, now in real life, meaning on my tests and also in real life, the question would be, give the organic product or products for the following reaction. Oh no, what do I do? Well, you look at a molecule, look for what's different. What's not carbon, what's not a hydrogen atom, what's not a carbon-carbon single bond should get your attention like this. I love my little red whistle. By the way, the company that made this from West Germany years ago went out of business. I luckily bought 5 of them. They're in my house and they'll never leave my house because they're too valuable. I like them. So what do? You look for what's different. What's different? A double bond. As soon as I see that molecule, all I see now is this. What am I reacting with? Hydrogen gas, H2, and what's nickel? A catalyst. And the catalyst can be nickel, which it is, platinum, which is not in this case, or palladium. And what happens? You break the pi bond. Remember, this is one pi bond and one sigma bond, single bond. Notice here I have 2 lines. Here I only have 1, so I've broken the pi bond, and each carbon gets a hydrogen. Now, do you break carbon-carbon single bonds? No. So I have 1, 2, 3 carbons. I better end up with 3 carbons. Here are my 2 carbons with the double bond. Notice here I have 2 lines. Here I have 1 bond, 1 line, and each carbon of that double bond gets a hydrogen. And now I know there are 4 bonds to carbon, and I can put in the hydrogens. Now you can write the answer like this, or if you notice on this carbon, there's actually 2 hydrogens. So I can write it this way. And this carbon, I have 1 plus 2, 3 hydrogens. Now, let's call this A. Let's call this B. Which way can you write on the test? Both. Now, in class, I'm going to write it this way, where I don't bring the hydrogens up to the carbon, because it's easier for you. And it's easier for you when you take a test. It's one less thing you can get a mistake on. But if you want to write it as B, propane, both are propane, I'll accept that. So let's go through it again. How do we figure out what's the product or products for following reaction? You look for what's different. Double bond. What am I reacting with? Hydrogen and catalyst. You have memorized this is the reaction you need to know to do this type of problem. Double bond plus hydrogen and catalyst. The catalyst can be nickel, platinum, or palladium. You break the pi bond, and each carbon of the double bond gets a hydrogen. Then you know you don't break carbon-carbon single bonds. I start with 3 carbons. I better end up with 3 carbons. I break the pi bond, and each carbon of double bond gets a hydrogen. Now, sometimes because of space, and I do this in a classroom too, I can bend the arrow, which I've done here. And it's your turn. Give the organic product or products for the following reaction, 3 points each. And now we're getting into the good stuff. And I'm happy. Nomenclature is important, but this is the fun stuff. All right, I think everybody's done. Let's do it. Now, we look at the starting material. What's different? What's not a carbon? What's not hydrogen? What's not a carbon-carbon single bond? A double bond. What am I reacting with? Hydrogen. And what's platinum? It's a catalyst. And a catalyst can be nickel, in our case, platinum, or palladium. And what happens? You break the, remember, there's a pi bond, you should know this, and a sigma bond and a double bond. You break the pi bond, each carbon of the double bond gets a hydrogen. Do you break carbon-carbon single bonds? No. So we start with 1, 2, 3, 4, 5. We better end up with 5 carbons. I break the pi bond. That's why there's only one line between these 2 carbons, and each one, our general reaction tells us gets a hydrogen. And there are 4 bonds to carbon, so I can put in the remaining hydrogens. And that's how you do it. Oh, let's try one more. I'm gonna see, why don't you try this one? All right, looks like everybody's done. And let's do C. And if we look at, oh, we've got a ring, but that's just carbon-carbon single bonds. But there's a double bond between these two carbons, two lines, double bond. And I'm reacting it with hydrogen gas and palladium as a catalyst. And the catalyst can be nickel, platinum, or in our case, palladium. And you break the pi bond. Remember, double bond is one pi bond, you should know, and one sigma bond. And how do we know we break the pi bond? Because there's only one line, and each carbon gets a hydrogen. Do you break carbon-carbon single bonds? No. So I have my ring, and I have my methyl group on the ring. Here are my two carbons of double bond. Notice I only have one line because I broke the pi bond. And technically I'm done because we don't show hydrogens. Now, if you did this, I'd laugh and say you really should put two hydrogens there. Well, let's take a look at this. We look at this carbon, we don't show it, but how many hydrogens on this carbon? Well, I've got 1, 2, 3 bonds. 4 minus 3 is 1 hydrogen. Same down here. Now, if we look at the same hydrogen in our carbon, our answer, I have 2 bonds to it. And that means there's 2 hydrogens. So it has happened where I add a hydrogen. Now, either one of these I accept on a test. Really, you should write it this way. Now, before I start telling students you don't break carbon-carbon single bonds, most of them would somehow break that ring, make it an acyclic compound, which means I'd mark it wrong. So you don't break carbon-carbon single bonds. Now, quick Dr. White story. And we got time real quick. Well, I know something. I looked at it. Let's take a 5-minute break and you'll have to come back. Cliffhanger time for a good Dr. White story. At least I think it's good. So let's take a 5-minute break. I'm going to get up and stretch, and I'll see you in 5. let's get back to work. But first, let me try to do something real quick. All right, let's get back to work. Now, I told you I was going to tell you a quick story. When I started in the chemical industry, right from academics, after I got my PhD, then I was a postdoctoral fellow for a year and a half at University of Illinois, Chicago. I started my first job. And my first project was dealing with a hydrogenation of a different molecule with a double bond in it, and actually more than a double bond. And I'll talk about this later in the semester. So I went in, my boss told me, here's your project, here's what you're trying to do. And I said, all right, thanks. And I sat down and I thought, all right, I'll do this and this. I went and talked to him before I started doing the research. And I said, well, I'll use hydrogenation with a platinum catalyst. And he smiled at me and started laughing. Actually said, did you look up the price of platinum? Remember, we're in industry now, and how much things cost to make are important, or we can't sell them. So I went and looked up, and he said, look up the price of nickel too. He already knew the answer. And nickel is about $5 a pound to use. Platinum or palladium is a couple $100 a pound. And when you use it, you lose some when you recover it. Certain things you just can't. So because the difference in prices, if you're in academics, well, you don't care about that. You use platinum or palladium, and certain pharmaceuticals where the profit margin is wide, you can get away with it, but in industry, use nickel. All right. So again, the general reaction is double bond, hydrogen and catalyst be nickel, platinum, or palladium, and you break the pi bond, and each carbon gets a hydrogen. Now, let's do one more. And here's one more for you to do. Question is, give the organic product or products for the following reaction. I made a mistake. Nope, I got this right. Each one of these carbons has a CH3 group on it. And it's my turn. Now, one of the tricks organic chemists do on the test, teachers who teach organic chemistry, and I do too, the favorite trick is put a big, scary molecule. And if you don't know how to look at a molecule properly, you go, eek, Hopefully you don't go eat, but you might. And if you look at D, it's a big, scary molecule. If you don't know what's different, look for what's different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond should get your attention like that. And all I see that's different is a double bond. As soon as I see that, everything else is coming along for the ride. And the only thing that's important is that. That's the functional group. And that's the beauty. And I truly mean it. The beauty and the power of learning organic chemistry is set up by functional groups. And what am I reacting with? Hydrogen gas, H2, PT, platinum is a catalyst. And a catalyst can be nickel, platinum, or palladium, PD. And what happens? Remember, this is one pi bond, double bond, and a sigma bond. Pi bonds, you break like that. Sigma bonds, you don't break carbon-carbon single bonds. So I'll break the pi bond. Each carbon gets a hydrogen of the double bond. Well, if I look up here, I have 1, 2, 3, 4, 5 carbons across. On this carbon, I have 2 methyl groups. You're not going to break those carbon-carbon single bonds. On this carbon, I have a methyl group. Here are my 2 carbons of the double bond. Notice I broke the pi bond. There's only one line between it, a single bond, and each one gets a hydrogen. I know there are 4 bonds to carbon, so I can now fill in the rest of the hydrogens. Remember, it's your solemn responsibility to make sure I've done this correctly. And even when you see me do a general reaction like this, that I've done it correctly, which I won't. And that's how you do it. Remember, all the fun, all the action is where there's a functional group, where something different. What's not a carbon-carbon single bond or carbon or hydrogen atom, that's where the fun's going to be. That's the action. Now, if you notice the way I've done this problem, on a test, some of my best students always write the general reaction underneath. On a test, some of my best students never write the general reaction, but they've learned this. You can do either one. That's in my head. As soon as I see, I'm trying to point here, as soon as I see this double bond, I think it's right over here stored. This general reaction pops up. Oh, it's back working again. I changed the battery. Wait, oh, that was a bad joke. But anyways, I see this reaction. I know I'm going to break the pi bond. Each carbon gets a hydrogen, and the rest comes along for the ride. Now, one of the nice things about having organic chemistry with an instructor who's worked in the chemical world and knows the real world of organic chemistry, you should always be asking me the question, or I will too, why am I learning this stuff? Well, the obvious answer for you is you want to get a good grade because somebody said you have to take this class to get into a program like nursing or other programs like physician's assistant or get into school. But why learn this? Well, this reaction, later on, you'll learn. How many of you have ever heard of hydrogenated fats and oils? Well, you do the same thing to double bond. And when we get into that, I have a story there, because years ago, I worked for a company called Unichem Chemicals. I was their research development and quality control manager for all of their research and plants in North America. And they were a part of Unilever. That's a company like Bird's Eye Food, and I can't believe it's butter. And I have a story about that in hydrogenation, but not now. All right, so the first general reaction you've learned, and you should memorize. How do you do this? Write it down 5 times and say it each time. Double bond, hydrogen catalyst, nickel, platinum, or palladium. Break the pi bond, and each carbon double bond gets a hydrogen. Remember, this is a building block, a tool organic chemists use to make things you use in your daily life. You can tell this is more exciting than nomenclature, but nomenclature is an important part. Oh, hold on. I thought I had tried something. That didn't work. So this. What happens is I get too many files open or something when I use my whiteboard, and Word locks up. All right, we're back on track. So we've learned you've learned hydrogenation. I already know it. Let's move on. Let's talk about halogen gas. Now, before I talk about halogen gas, or called halogenation, let's go to the internet. Does everybody see the periodic table on your screen? Give me a thumbs up if you can see it. Thank you. And if you look all the way here where it says the halogens, and the halogens are fluorine for this class, chlorine, bromine, and iodine. I'll never ask you what's a halogen, but henceforth, when I say the halogens, I'm talking about fluorine, chlorine, and bromine. Now, the other two, or others, I've never used. I don't even know how to pronounce it, astatine and tennessine. I've never used, and they're not used in an everyday organic, but the halogens, fluorine, chlorine, bromine, and iodine are. So let's look at halogenation of a double bond. And here, organic chemists somehow decided, use the letter X. X means fluorine, chlorine, bromine, or iodine. And later on, sometimes you omit fluorine, but for now it does. So whenever you see X, that means the halogen, fluorine, chlorine, bromine, or iodine. And X2 means 2 chlorine, 2 fluorine, which is how it exists in nature. It exists as a diatomic molecule. And here, oh, by the way, R prime is like X and Y, and we'll talk more about it later in the semester. But if I have any double bond, remember 1 pi bond, 1 sigma bond, and reacted with a halogen. Now here you don't need a catalyst because the bond energy is involved. This goes quick. I mean quick. And you break the pi bond, and each carbon of the double bond gets a halogen. Remember, X here equals fluorine, chlorine, Cl, bromine, Br, or iodine. And this is a general reaction you need to know. So let's take it out and practice with it. All right, let's try the following. Remember, the question's going to always be, well, it's going to be on a test. And these are what I call reaction problems. Turns out organic chemists are very discriminatory against inorganic chemistry. I hated it. Of the branches of chemistry in general, I do not like inorganic chemistry. Shh, don't tell anybody. And the question is, give the organic product or products are the following. I'll do this one, I'm going to share the fun. The question is, how do I do this? Well, you look at a molecule, look for what's different. What's not carbon, what's not a hydrogen, what's not a carbon-carbon single bond. Get your attention like that. And I say, ooh, a double bond. I'm reacting it with bromine. And bromine is a halogen, which we abbreviated halogen gas, Br2, X2. Remember, X can be fluorine, chlorine, bromine, or iodine. And you break the pi bond, and one carbon of both carbons, the double bond, get a halogen. So do you break carbon-carbon single bonds? No. I start out with 1, 2, 3 carbons. I better end up with 3 carbons. Here are my 2 carbons of the double bond. I broke the pi bond. That's why you only see one line. Each carbon gets a halogen. My halogen is bromine, not Br2. That's a common mistake students make. And this counts as a bond to carbon. We look at this carbon right here as 3 bonds, which means it has 1 hydrogen. We look at this carbon has 2 bonds, which means it's got 2. Now, another way of writing this, which I don't expect you to do, but if you look on the internet, you might see it this way. This is a better way for you to not make a mistake. And that's how I'd recommend you do it on a test. Either way is acceptable though. So what do? We look for what's different, double bond. What are we reacting with? Bromine gas, Br2. The general reaction, double bond, halogen gas, where X can be fluorine, chlorine, bromine, or iodine. To break the pi bond, each carbon gets a halogen atom, not 2, 1. And you don't break carbon-carbon single bonds, 3 carbons, 2 carbons of the double bond gets the halogen. Now, let's be I need to talk about something very important. Notice how these 2 bromines are adjacent. Notice this is called 1,2 disubstituted bromo, be 1,2 dibromo. I don't go until I'll go later on when we get into aromatic compounds into halogen nomenclature. This is 1,3. This is wrong. You don't get this. Therefore, placement of atoms in organic chemistry is very important. Up here, that's correct. Down here, this is wrong. So make sure you're careful where you put new things adding to a molecule. It's sort of like you're not going to draw somebody's nose on their face over here. It would be wrong. Well, putting the halogens or atoms in the wrong place in my class and in real life is wrong. And here's one for you to have fun with. Give the organic product or products for the following reaction. All right, it looks like everybody's done, so it's my turn. If we look at this molecule, first thing is look for what's different, what's not carbon-carbon single bond, carbon or hydrogen, and that should get attention like that. And it did. I have a double bond. Now I'm reacting it with iodine, I2 iodine, gas or solid. And what is iodine? I really should have done this. Sorry about that. Let's back up. Double bond. Iodine is a halogen. This is halogen gas. Remember, X can be fluorine, chlorine, bromine, or iodine. And you break the pi bond. Remember, double bond, you should know, hint, you should know, is one pi bond, one sigma bond. Sigma or single bonds you don't break. Each carbon of the double bond gets a halogen, X. In this case, X is iodine, I. You break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5, 6. I better end up with 6 carbons. Which 2 carbons are the carbons of the double bond? Those 2. Which are these 2? 1, 2, 3, 1, 2, 3. You want to do it that way to make sure you know. And each one gets a halogen. In this case, it's iodine. I know there are 4 bonds to carbon, 1, 2, 3, 4. So I can do my math to put in the number of hydrogens. Remember, halogen counts as 1 bond to carbon. And here you've made that compound. Again, double bond, halogen gas, break the pi bond, each carbon gets a halogen, and you don't break carbon-carbon single bonds. No, you don't. Oh, let's do one more. And here's one more for you to have fun with. Give the organic product or products for the following reaction. 3 points each. By the way, you're doing the fun part of organic chemistry, at least for Dr. White, me. All right, my turn. If we look at this molecule, what's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? I have a double bond in a ring. I'm reacting with fluorine. F is fluorine. Gas, that's F2. And that's halogen gas, which organic abbreviate by chemists by X2. Remember, X can be, in our case, it is fluorine, chlorine, bromine, or iodine. And if you break remember you break the pi bond, but not the sigma bond, and each carbon of the double bond gets a halogen. Do you break carbon-carbon single bonds? No. So I have a ring, still going to be a ring. There's still going to be CH3 methyl groups. And these two carbons, notice I only have one line. I broke the pi bond. And each one gets a halogen, in this case, fluorine. Now, you could have also written it this way, which for this class would have been acceptable. Let's call it A or B. Either one would be acceptable. So what happened? We broke the pi bond because we saw it's a double bond. Fluorine gas, F2 is a halogen. Break the pi bond. Each carbon of the double bond gets a halogen. So I have my ring and my two methyl groups. Then I broke the pi bond there, and each one gets a fluorine. And that's halogenation. Now, as I said earlier, I learned this, and the obvious reason is you want a good grade. Well, why learn about halogenation? Well, it turns out by replacing hydrogens in a molecule with halogens, it makes it less flammable, otherwise known as flame retardant. There's no way you can make something that could burn flame proof, but you can make it flame retardant. And where is that important? Children's bed clothing and children's clothing, but especially their sleepwear. And years ago, children were getting burned very badly by getting near a candle when they're at night in their bedclothes, or near open flame, like in a stove, or a stove top with a gas flame, or other near a heater, space heater that gave off a lot of heat, and their clothing would catch fire. Well, it turned out by putting halogenated compounds on the cloth, it makes it flame retardant. It doesn't burn as quick, which saves the child. Now, interesting thing, about 4 years ago, for many years, things that were made like couches and plastics, like your monitor I have in front of me, my mouse, by the way, this is a Death Eater mouse, Death Adler, not Eater. It's a really good mouse. I've had this for a couple of years. But anyways, a couple of years ago, I think it's been about 5 or 6 years ago, 4 very, very ingenious or very determined reporters from, I think it was the Chicago Tribune, or sometimes, I think it was Chicago Tribune, investigated flame retardants. One of the problems with halogenated compounds is they're also, some of them, smaller ones, carcinogenic, cause cancer. And they found that a lot of the chemicals that were being sold for things like plastics didn't do a job. And they were getting into the air and they could cause cancer. And they brought that to everybody's attention. And the reason why most people, halogenated compounds, they stop fire, got fooled is the companies that sold additives for things like plastics took a report by the Swedish chemist and misinterpreted it on purpose. And actually, they made conclusions that weren't true from the report. And that's what these reporters were able to do, go back, look at that report, talk to people and find, no, that really doesn't do what these companies were saying. Now, in California, I don't know if it's hit to Illinois, a lot of these have been banned. Now, one other thing, and this is a public service from me, Dr. White, to you, is how many of you have heard of dry cleaning? I don't wear a coat and tie anymore and a fancy shirt, so I don't go to dry cleaners that often. When I worked in the chemical industry, my uniform was a coat and tie and a nice shirt, which all had to be dry cleaned, pants too. Now I just throw everything in the washer. But anyways, what's a dry cleaner? Well, they don't use water when they clean the clothes. They use organic solvents. And for many years, they used chloroform and carbon tetrachloride, along with, I'll teach you, surfactants. Switch is totally off now. This has the common name chloroform. Well, there's a case where a tetra meaning 4. And chloroform and carbon tetrachloride, I use the slang organic chemists use for carbon tetrachloride without even thinking carbon tet. But anyways, they were very good solvents for dry cleaners. The only thing is, these are very, very dangerous carcinogens, cause cancer. Well, it turned out back in the 1940s and 50s, when pollution laws weren't that strict, they were almost non-existent. The EPA wasn't in existence yet. Environmental Protection Agency, I think that came in the 1970s. Dry cleaners couldn't dump this down the drain because of the density of chloroform or carbon set. It would just sit in their drains in their building. So what did they do? They found an open field near their dry cleaners, took the waste solvent from after they washed clothes, collected it, and dumped it in empty fields. Yes. Now, they can't do that anymore, and they don't. But the reason I'm telling you this is in Chicago, there are a lot, I don't know how many hundreds of what's called Superfund sites that were near dry cleaners that these people did them. And the reason I'm telling you this, when I bought this house, I was looking for a new house. I checked and made sure in a couple mile radius, was there any old dry cleaners where they dumped stuff? And you can look up Superfund sites in the United States or in Chicago on Google or through your favorite search engine. Mine's Google. I guess the commercials, if you do use, was it DuckDuckGo, so they don't know what you're looking at. But anyways, look and see if there was a Superfund site, because you don't want to buy a property near that, because they've slowed down because of the money, lack of money. You don't want to be near a site that has carcinogen in it. Unfortunately, there are good sides of chemistry and bad sides of organic chemistry. All right, so that's halogenation. Now, one of the things that if you look at this reaction, and let's just use halogenation for an example, and hydrogenation, these are symmetrical addition reactions. To each carbon of the double bond, I'm adding the same thing. Here it's a halogen. Here it's hydrogen atoms, but it's the same. What happens if it's something different? And that's called unsymmetrical addition reactions. Now, unsymmetrical addition reactions, what you see on the screen, don't write down. Now, I'll explain why in a second. But unsymmetrical addition reactions follow the great Russian chemists, and we use a chemist's name, organic chemists, when they've made great discovery to honor them. And that follows Markovnikov's rule. And Markovnikov's rule is when an unsymmetrical molecule to form HA and H or HQ adds to unsymmetrical alkene, double bond, the hydrogen from HA or HQ becomes bonded to the unsaturated carbon atom, that's the one double bond, that already has the most hydrogens. And if you look at Markovnikov's rule, you go, what? Well, let me show you how to understand Markovnikov's rule. Oh, by the way, switch is now on. It was for hydrogenation and halogenation. And let's look at addition of an acid, a hydrohalogen acid, to an alkene. Now, I have it written here one way. A better way to write it is this way. One of these days, I'll change these slides. In this case, X equals not fluorine, because HF, hydrofluoric acid, is a very, 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 very dangerous chemical. In fact, of all the projects I worked as an industrial chemist, only one that I refused to work on. That's where they wanted me to work on HF. And I already established a project with HF, hydrofluoric acid. And I said, no, I'll quit before I work on that, because I already done enough. They found someone else, and he almost had a nervous breakdown working with that stuff. HF, hydrofluoric acid, you get it on your skin. It goes right through your skin all the way to the bone. Bad stuff. But anyways, for this reaction, take a double bond, react it with an acid HX, where X can be chlorine, bromine, or iodine, You break the pi bond, one hydrocarbon gets H, the other gets X, the halogen. How do you know which? It follows Markovnikov's rule. Now, I used to spend all the time writing out Markovnikov, and I'd spell it wrong once in a while. And I just put down M's rule. So let's look at what's Markovnikov's rule. How do you apply this reaction? And the question is, give the organic product or products for the following reaction. And what do you see here that's different? A double bond. Reacting with hydrochloric acid, remember halogen is abbreviated by X. Remember, for this reaction, X is chlorine, bromine, or iodine. I'll never play a trick on you because I don't do that. It's wrong. It's against my golden rule of teaching. Don't do to students what you haven't done, didn't like done to you. Also, on every problem on my test, I'll explain the concept behind that at least twice, usually a lot more. So remember, double bond, one pi bond, one sigma bond. You break the pi bond, one carbon gets H, the other gets X, and it follows Markovnikov's rule, that great Russian organic chemist. Now, do you break carbon-carbon single bonds? No. So I'm going to have 3 carbons. I broke the pi bond. Now, which of these 2 carbons gets the hydrogen and which gets the halogen? Well, here's where you follow Markovnikov's rule. The carbon with the most hydrogens, atoms on it, gets the hydrogen. The carbon with the most hydrogens gets the hydrogen. Now you got to use high-level math. This has 2, this has 1. Which of those numbers is greater? Hopefully you all pick 2. So Markovnikov's rule says the hydrogen goes here, and the other carbon gets the halogen, chlorine. And that's how you do it. Now, if you have those switched, put the hydrogen on carbon 2 and the chlorine on carbon 1, I'll mark it wrong. Because that's called the anti-Markovnikov product, which there's ways of getting that. I won't teach that in this class. So let's go through this again. We have a double bond. We're acting with HCl, hydrohalogen acid, hydrochloric acid, HCl, and X is a halogen, double bond, HX. Your X can be chlorine, bromine, or iodine. You break the pi bond, one carbon gets H, one gets X, and it follows Markovnikov's rule. Markovnikov's rule is look at the 2 carbons of the double bond. The one that has the most hydrogen atoms will get the hydrogen from HX, and the other gets the halogen. This carbon has 2, this has 1. My hydrogen goes there, my chlorine goes there. And that's how you use Markovnikov's rule. Now, when I learned organic chemistry as a sophomore at IIT, I had a really good instructor. I still remember this decades later, and he taught us to remember organic, to Markovnikov's rule. Think of this way. 1, the rich get richer and the poor get poorer. And what was he talking about? Not money, but hydrogens. Remember Markovnikov's rule, the rich get richer, the poor get poorer. In other words, the hydrogen goes to the carbon and double bond with the most hydrogens, and the halogen goes to the other carbon. He also taught another way, and it's not good English, but I still remember, don't ask me why, but it works. Them that has it gets it. And again, we're talking about the hydrogens. Them that has it gets it. The carbon of the double bond with the most hydrogens gets the hydrogen from HX, the other one gets the halogen. But I still like the rich get richer and the poor get poorer. And here's one for you to try. What would be the organic product or products for the following? 3 points each. Now we're doing some serious organic chemistry, and I mean that. This is high level stuff. Oh, in about 2 weeks, if you're at a Super Bowl party, don't talk about Markovnikov's rule because people don't like hearing about organic chemistry at Super Bowl parties. All right, looks like everybody's done. My turn. So if we look at this molecule, look for what's different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond, a double bond. I'm reacting with HBr, and halogens are X. X can be chlorine, in our case it's bromine, or iodine. Break the pi bond. Remember, double bond is 1 pi bond, 1 sigma bond. And 1 carbon gets the hydrogen, 1 gets the halogen, and it follows Markovnikov's rule. The carbon double bond with the most hydrogens gets the hydrogen, the other carbon gets the halogen, otherwise known as the rich get richer, the poor get poorer. So if we come up and look at this molecule, this carbon has 2 hydrogens. This one has 0. Which is the larger number? And hopefully I'll pick 2. So what does that mean? Do you break carbon-carbon single bonds? No. So I have 3 carbons plus the methyl group. Here are my 2 carbons of a double bond. I've broken the pi bond, and 1 carbon will get the hydrogen. Which one? The one with the more hydrogens. That's Markovnikov's rule. The other will get the halogen, and I'll put that on top. And I know there are 4 bonds to carbon, so I can put in, and that's how you follow Markovnikov's rule. Again, double bond, reacting with HBr, halogen is X. You break the pi bond, 1 carbon gets the hydrogen of the double bond, the other gets the halogen, and it follows Markovnikov's rule. The carbon of double bond with the most hydrogen gets the hydrogen, the other carbon gets the halogen. High level math, this carbon has 2, this has 0. The hydrogen goes to the carbon with the more hydrogens, and the other carbon gets the halogen. And that's how you do it. Oh no! We've run out of time. Time flies when you're having fun with Markovnikov's rule and Dr. White. All right. Thank you for joining me for an exciting afternoon of organic chemistry with me, Dr. White. Remember, on Tuesday evening at 6 to 7:15 and Wednesday from 6 to 7:15, I have my office hours. You can always email me. And with that, I'm done for today. And I'll use the Yiddish words, which I started in the beginning of the pandemic. Gehen gesund, going hell, still bad out there. The flu and other things are floating around. I'll say, goodbye, I'm done. I'll post the video later today or tomorrow. Bye, game gesund. I stole that from Granny, the Beverly Hillbillies.